This is a story that I'd call The True History of Infinite Series, starring Socrates and Amphibians. You will play the part of Socrates, and Amphibians will play the part of himself. This is a dialogue, so please keep in mind, when it comes to your part, please speak along, and I will help you. And just follow along with Amphibians. Feel free to take notes as we dialogue. The True History of Infinite Series. Through painstaking research, I have traced the beginnings of infinite series to ancient Greece. I have discovered a lost manuscript about the greatest philosopher of all time. Though long since forgotten, at one time he was so great that people called him Socrates. This manuscript describes a dialogue between Socrates and one of his students, Amphibians, who was always hopping all over him with questions. Throughout the following reconstructed dialogue, notice how Socrates employs the Socratic method, by which the student is brought to knowledge through queries such as, "What's so great about that?" Remember, you are playing the part of Socrates, which I will assist you with, and Amphibians will be playing the part of himself.
Oh, great Socrates! I've been studying sequences back at my pad, and I have sudden urge to dive into infinitely serious harmonies.
Perhaps you misunderstand the realization that the infinite harmonic series diverges, Lilyhopper.
Seriously? What does that have to do with sequences?
A series is just the sum of the terms in a sequence.
That sounds pretty significant. So if I wanted to add all the terms of the sequence, 1 over 3 to the k equals 1/3, 1 over 3 squared, 1 over 3 cubed, I would use a series?
Actually, an infinite geometric series in this case, with a finite sum.
I thought the infinite series was the prediction that by the Oracle at Delphi that Chicago Cubs are forever destined to never be in the World Series. Fooled you. You mean that the sum as k goes to 1 to infinity of 1 over 3 to the k is equal to 1/3 plus 1 over 3 squared plus 1 over 3 to the third has a finite sum?
Yes, Tadpole. Some infinite geometric series do have finite sums.
What does geometry have to do with anything? And how do I find some sums?
A geometric series is where each term is found by multiplying by a common ratio. To find the sum, you simply find the limit of the partial sums.
Partial to some sums? That sounds a tad politically incorrect. Shouldn't a great guy like you be partial to all sums?
The sequence of partial sums is found by adding the first term, then adding the first two terms, then adding the first three terms, etc., etc., etc.
Okay, so the sum of the first term is 1/3. Hey, I can even do that without my TI 84 BCE. The sum of the first two is 1/3 plus 1 over 3 squared equals 1/3 plus 1/9 is equal to 4/9. And the sum of the first three is 1/3 plus 1 over 3 squared plus 1 over 3 to the third equals 4/9 plus 1 over 27 is 13/27. Hey, it looks like a pattern. It's always less than 1/2.
So what would be the sum of the first 100 partial sums?
Even a reptile can see that it's 1/2 times the quantity 3 to the 100th minus 1 over 3 to the 100th, which is equal to 1/2 times the quantity 1 minus 1 over 3 to the 100th.
And what would the explicit formula for the sum of n terms be?
Looks like 1/2 times the quantity 3 to the n minus 1 over 3 to the n, which is equal to 1/2 times the quantity 1 minus 1 over 3 to the n. And the limit, as n goes to infinity, of that is 2. 1/2, sorry.
What's so great about that? If the series is infinite, you will always be leaving off the tail.
Hey, watch the leaving off the tail jokes. The tail of the tail is found by examining the remainder. So, for s sub 100, the sum of the first 100 terms, the remainder is r sub 100, which is equal to the summation, as k goes from 101 to infinity, of 1 over 3 to the k, which would seem to be rather negligible.
Since it is a geometric series, you can use a formula to figure it out. For example, for any geometric series, G sub n is equal to A plus AR squared plus AR cubed plus etc., AR to the n minus 1. We could take R times G to the n, which is equal to AR plus AR squared plus AR cubed plus etc., plus AR to the nth. Then G sub n minus R times G sub n is equal to A minus A times R to the nth. So G sub n times the quantity 1 minus R is equal to A times the quantity 1 minus R to the n. And G sub n will equal A times the quantity 1 minus R to the n over 1 minus R.
So R sub 100 is equal to the summation as k goes from 101 to infinity of 1 over 3 to the k is equal to the limit as n goes to infinity of 1 over 3 to the 101st times the quantity 1 minus 1 over 3 to the m over 1 minus 1 over 3, which is equal to 1 over 3 to the 101st times 1/2, or 1 over 2/3, which is equal to 1 over 3 to the 101st times 3/2, which is equal to 1/2 times 1 over 3 to the 100th, which is pretty darn negligible if you ask me.
I didn't ask you, but does this series converge or diverge, Tadpole?
Well, R sub n, the remainder, is equal to the summation as k goes from n plus 1 to infinity of 1 over 3 to the k, which is equal to 1/2 1 over 3 to the n using the same logic.
And what do you know about that sequence?
It is decreasing because of the no-clue theorem. You know, the derivative.
The what? You must have been talking to Diogenes again. Drat that, falsify the currency.
And is bounded below by 0, since it's always positive.
So what does this tell you?
The tail disappears because the limit as n goes to infinity of R sub n is equal to 0.
Yes, it is 0, but be careful. 0 factorial is equal to 1.
I should have guessed that the series converged because the limit as n goes to infinity of 1 over n is equal to 0.
That is actually a necessary but not sufficient condition for convergence. This is called the nth term test for divergence. But what will it converge to?
Well, all I need is a formula. G sub n is equal to A times quantity 1 minus R to the n over 1 minus R. Because the limit as n goes to infinity of S sub n is equal to 1/3 times the quantity 1 minus 1 over n over 1 minus 1/3 is equal to 1/3 over 2/3, which is 1/2, just like I said before.
You are correct. The sum of the whole series is 1/2.
The whole is 1/2? That's rather confusing. Will this work for any infinite geometric series?
Provided the absolute value of the ratio is less than 1, then the formula, the limit as n goes to infinity of G sub n, is equal to A times the quantity 1 minus R to the n over 1 minus R, which is equal to A over 1 minus R, because the limit as n goes to infinity of R to the n is equal to 0 when R is between -1 and 1.
But what about this infinite harmonic series that you said diverges?
The infinite harmonic series is the summation as n goes to 1 from 1 to infinity of 1 over n is equal to 1 over 1 plus 1 over 2 plus 1 over 3 plus etc., etc., etc.
But since the limit as n goes to infinity of 1 over n equals 0, doesn't this have to converge too?
Remember, that is a necessary but not sufficient condition for convergence. If it were not true, we would know it diverges, but we cannot conclude that it converges. Consider grouping the terms in the following way. 1 over 1 plus the quantity 1 over 2 plus the quantity 1/3 plus 1/4 plus the quantity 1/5 plus 1/6 plus 1/7 plus 1/8 plus etc., etc.
So you are always doubling the size of the group, other than the first one. What does that tell you?
Compare it to 1 over 1 plus 1 over 2 plus the quantity 1 over 4 plus 1 over 4 plus the quantity 1 over 8 plus 1 over 8 plus 1 over 8 plus 1 over 8.
Oh, I see. It will always be greater than 1 plus 1/2 plus 1/2 plus 1/2, which obviously diverges. Sneaky. So the infinite harmonic series doesn't converge because a sequence of its partial sums diverges. Wow, that is fantastic.
What's so great about that?
Don't you see the series ramifications? Since serious harmonies diverge infinitely, I can sing off key whenever I want. And because I can tell which geometric series converges by simply looking at the ratio, no more of those messy two-column proofs. There is no limit to the possibilities, and I owe it all to you. I can't wait to get back to my pad and do some more sequences of series.
And that is the true history of infinite series. Honest.